Okay,
There it goes.
we're live. So we're group 4. I'm Keegan, and this is Penny. And we're going to go through those problems with you. I'll pull up my paper, and we'll go through it. Penny's going to do number 1. So
the first question, determine the allele range parent. You look at the parental. Parental are always the two most numerous. So we see these two right here that are marked. So that's how we came up with the parental, the allele arrangement for the heterozygous parent. Now to determine the gene order, you look at the double crossovers, and those are always the two least numerous. And I always, hopefully this focuses for a second. Here it is. So I draw them out with the top alleles in the 3 different orders. And then you find the orders when you cross them over, and I draw these funny little boomerang shaped thing, that's good, Keegan, around them to find the ones that match the alleles for the double crossovers. And that's how we're able to find out that A is in the middle for this one. And once you find out what's in the middle, you can find out the distances. So to find the distances, you find the distance between the MG and the A alleles, plus your double crossovers, divide that by your total number times 100 to get 13.1 and 17.5. And to calculate the interference, so you take your 13.1 divided by 100 times 17.5 divided by 100, and then multiply that again by 100, and that gives you your 2.3% is how many should be crossovers. So then you multiply that by your total number. So in this problem, 4.74 of the samples should have been your double crossover. So then we take what we did have, which was 2 divided by 4.74 equals 0.42. 1 minus 0.42, and you get that's where we get the 58%. Have anything to add to that one, Keegan?
no, I think that's good. And then I tried to show the work there, so if anyone needs to go back through it, and we'll probably be a little quicker on 2, 3, and 4 because it's all kind of the same. It's just a pattern. So moving on to 2, same thing. We have the chart. I found these two with the P. They're the parental offspring. And so that's where I get the SC wild type and then SV, and then just the opposite for, that's the gene arrangement. Then you go down to the gene order. I did the same thing. I put them on top of each other, and I drew what they would look like with those arrows if we did a double crossover. And so I got that the SC gene needed to be in the middle. So we got that one that's highlighted green. Then you move down once you have that information, and you can do the linkage maps. You have the double crossovers, 10 and 14, that'll be in both equations. And then the S to SC is 30 and 46. And the SC to V is the 150 and 156. Add those all together, you get 10 and 33. Bring this down and to find the interference, and you get a 3.3%. Take that into the 1,000, you get that there should be 33 of them. We actually saw 24, so 24 divided by 33 equals 0.73, which gives us an interference of 27%.
All right, this one was a little more trickier because there are no double crossovers. Yeah, there are no double crossovers, and once we were able to determine that, it makes a little more sense. So first, you can identify the 3 linked genes for the parental by looking at the 2 most numerous, and for that we get C in G plus S plus on the top and G C plus S on the bottom. Now for the gene order, we determined that the S was in the middle because the striped thorax gene is different. So we kind of compared all the patterns of them, and that's why we decided to put the S in the middle. And once we were able, because we didn't have the double crossover to determine and to do the crossover trick that we like to do, but then we came up with 1.9 and 5.6 MU for the distance. And because there were no double crossover, you're dividing 0 by 100, so you get 100% of the expected crossovers did not occur. because we expected.
Sorry. Yeah.
You're good.
So 4, moving on, same thing. We had BR, FA, and wild type over BR, wild type, F, wild type, AN. Then we did the same crossover that we did because we could do it on this one. And we found that the F needed to be in the middle. So we chose that first one that's green. We brought that down. The 2 and the 3 were the DCOs, or the double crossovers. So those stayed the same in both equations. And then the B to R, BR to F was 20 and 26. And then the F to AN was the 87 and 98. Did that math. We got 5.1 and 19. Bring that down, same equations before. We got 0.97%. So we expected to have 9.7. We actually had 5.52, which in turn 1 minus 0.52 is 0.48, or 48% interference for that one. Now question 5.
All right, for this one, since we're talking with independently assorted genes, we expect a 1:1:1:1 ratio of the big A, big B, little a, big B, big A, little b, little b, little b. So quarter for each one of those. And suppose those are linked, we would expect half of them to be big AB and half of them to be little AB. So a 1:1 ratio on that one as well, but not as many different phenotypes when they're not independently assorted.
Awesome. And then C, it just says, what are the possible genotypes? And so since big A is linked to big B and little a is linked to little b, you can have all 4. You can have just a homozygous dominant, 2 heterozygotes, and homozygous recessive. That question correlates to D. And so what I did is I did the heterozygotes. So I took the 7.8 divided it by 2. And so I gave those to the heterozygotes, which is 3.9% for each. Then I knew that the homozygous individuals would be equal, kind of like the parental genes. And so I just took 100 minus 7.8, which gave me 92.2, and divided that by 2, and assigned half to each, the homozygous dominant and the homozygous recessive. And so that is how we got the answer for D. So do you have anything else, Penny?
Nope, that's it. Thanks.
So, yep, I think I'll come up here, stop screen sharing, and we're good. So if you guys have any questions, you can just comment below and we'll answer them on the discussion board. So thank you.
Thanks.